In this chapter, we will be exploring exponential functions. In this lesson, we will be reviewing the exponent laws. And we will start with the multiplication law.
So the first of the exponent laws that we're going to look at, or we're going to review, because the assumption is at this point that this is material that you've gone over before. We're just going to try to go through and help you remember the rules before we go through and start to apply them in a new way here. So first rule we're going to look at here is the multiplication law. So if I've got x to the m multiplied by x to the n, okay, the result is that I get x to the m plus n, so I add the exponents. So here's the law. When the bases are the same, and that's really important. The bases have to be the same or else this doesn't apply. Then what we do is we simply add the exponents. We can also look at a few examples here. So if I've got x cubed multiplied by x squared, okay, then my result is going to be x to the power of, well, 3 plus 2 here, so x to the power of 5. It's actually quite simple, straightforward, but you got to remember when you do this. I'm multiplying two powers and the bases are the same. So here I am multiplying two powers, the bases are the same, 3 to the a times 3 to the b. Now, I don't know what the exponents are, okay? I don't know what a represents, I don't know what b represents. But that doesn't really matter. What I know is that when I multiply those together, the product could be found by simply taking 3 to the power of the sum of those two exponents right there. So 3 to the a times 3 to the b is 3 to the a plus b. And I would write it like that, and I would leave it like that. Now over here, this problem here gets done incorrectly frequently, very, very frequently. When you ask people point blank how to do this, kind of make them stop and think about it, now they get it. But if you put this in the context of a larger question, this little guy right here tends to be done wrong incorrectly all the time. S to the fifth times s. Well, what's the exponent if it's not written? The exponent is 1. So s to the fifth times s to the 1, okay, is going to be the sum of those two. This will be s to the power of 6, okay, to the power of 6. A lot of times people forget that there's a 1 there that needs to be included. Okay, that's an important question. Just little details there, but it makes a big difference. Over here, another thing to remember is that when you're adding those exponents there, that the rules that govern how integers work apply in the exponent as well as they do anywhere else here. So x to the 4 multiplied by x to the negative 2 will be a power of x, but what's the exponent going to be? Well, I got to add the exponents here. I got to add 4 and negative 2. 4 and negative 2 is going to be 2. So the response here has got to be x to the 4 times x to the negative 2 will end up being x squared. Good. So there you go. So just bear in mind, when you're multiplying powers with like bases, you add the exponents.
The division law.
So the division law says something really parallel to the multiplication law here. When I'm dividing two powers, okay, it doesn't really matter how I write it, but when I'm finding the quotient of two powers where the bases are the same, and again, here we go, when the bases are the same. This doesn't apply if we're talking about two powers with different bases here, but when they are the same, then the result is simply a power where the exponent is the difference between those two exponents there, okay? So basically I'm going to find the difference, or I'm going to subtract the exponents. So that's the rule for division. And again, the assumption is at this point that you've seen this before. We're just trying to remind you of this. So let's take a look at some examples here. X to the 5 divided by x squared. Well, that's going to be a power of x, and my exponent is going to be the difference between those two. So 5 minus 2, the answer is 3. So the answer to this would be x cubed. Over here, 3 to the m divided by 3 to the n. Now, I don't know what the exponents are, and that's not the issue here. The issue is the pattern, okay? It doesn't matter that I don't know what the specific numbers are there. What matters is that what I do because of the division there, and what I'm going to do there is take the two exponents and I'm going to find the difference of them. Now, do I know what m minus n is? No. But I do know that the exponent would have to be m minus n. So that's as far as I would go. That's my endpoint. Okay? Sometimes people wonder, well, how far do I take this? Well, right here, that's it. That's as far as we're going to be able to go here. Let's go down here. X to the 12 divided by x cubed. Okay, now this is written as you would most rational expressions. It's a lot more clear for a lot of people. And again, I'm dividing power, so I'm going to subtract exponents. So 12 minus 3 is going to be 9. So then the result here is a power where the exponent is 9. And then finally, and like we said with the multiplication here, the rules that govern how integers work also apply here. So what I'm going to do here is I'm going to get a power. It's going to have a base of x. I've got to the power of 4 to the power of negative 2. So this is going to be 4 minus negative 2. Okay, I'll write this up here. This will be 4 minus negative 2. That negative right there is the result of the division. That negative right there is because of the negative that's right here in the exponent. And so now this is going to get me x to the 6. 4 minus negative 2 is 6. You got to remember the rules of integers there. Okay? Now, one thing that I want to mention before we move on and take a look at a law that doesn't create this kind of difficulty is before we leave this, notice that when I did 3 to the m divided by 3 to the n, I didn't divide the bases out. I didn't go, 3 divided by 3 is 1, and then do something with the exponents. The only work that I did here was with the exponents. Just like up in the previous question when I went 3 to the a multiplied by 3 to the b, the result is 3 to the a plus b. It didn't become 9 to the a plus b. Okay, I don't multiply. Well, okay, I am multiplying, in essence, the bases together, but I do that by adding the exponents. That's how I perform this operation, not by multiplying the value of those two bases together. Please keep those separate here. When you multiply powers, when you divide powers, the work that you're doing is in the exponent, not in the base.
The power law.
Okay, now the power law. So the power law says that if you've got a power or an exponent on a power, okay, you would multiply the two exponents together. So x to the power of m, or x to the exponent m, and then raise that to the exponent n here, we would just multiply the two exponents together. Now, that's the power law, but it's a little bit more complicated than that. If you've got a product, okay, all raised to the exponent here x, the x distributes to every factor in the product. And just like here, if you've got a quotient, okay, if we're dividing two powers here, then the exponent on the outside here, outside of the brackets here, gets distributed to both of those powers, okay? So those a to the m divided by b to the n becomes a to the mx divided by b to the nx. Now, this is a rule that gets used all the time, but it's also a rule that gets misrepresented or misconsidered, I guess is the best way to say this, or misapplied maybe. Because there's another rule here, or sorry, not another rule, but there's a place where this rule gets applied where it doesn't apply. When you've got a plus b to the x, okay, this does not equal. And I know, and I've said this in my class like hundreds and hundreds of times, and yet we still get people that like, what? What? That doesn't seem right. No, yeah, you should, but it doesn't. It does not equal a to the x plus b to the x. That is not true. In fact, a plus b to the x is much, much more complicated than that. Okay, this is a ridiculous oversimplification of this particular expression here. This does not hold true in general, okay? Please don't do that. You cannot, if there's addition there, you cannot distribute the x, or even if it's subtraction. But if it's multiplication or division, okay, if this is a bunch of factors, this is a bunch of, like this is your divisor and your dividend there, yes, you can. Feel absolutely free to distribute that exponent through both of those factors, or the dividend and the quotient here, or dividend and the divisor. Now let's take a look at some examples here. So when I've got x cubed, and that's all squared, I'm going to just find the product of the exponents there. So this will become x to the 6th. Okay, x cubed squared, 3 times 2, 6. Here, because I've got two factors here, the 5 is going to essentially distribute to both of those. This becomes m to the 5, and then n to the 4 to the power of 5. And then, because I've got this power, and I've got an exponent on that, what I'm going to do here is make this m to the 5, and now I'll multiply those two together to get n to the 20th. Same thing here, I've got two different factors, so the square here, the exponent 2 will distribute to both of those. This will become 3 squared and then z to the 6 squared. And I can evaluate that. 3 squared is just going to be 9. That's easy enough. And then z, okay, and with an exponent of 6, and then that to the exponent 2 here is going to be z to the product of those two, z to the 12. Just multiply those two. And finally, this right here. This time I've got this quotient here. The 3 is going to distribute to both of those terms here. So this will be r squared cubed divided by 2t to the 5th. This is all going to be cubed. Now in my numerator, that's not such a big deal. That'll just be r to the 6th because I've got now a power of a power there. But in my denominator, I actually have to distribute the 3. Okay, because there's two factors in the denominator. So this becomes 2 cubed t to the 5th cubed. And now I got to do these two parts here. So we've still got r to the 6th in the numerator. 2 cubed is going to be 8. And then I've got a power of a power, so I'll multiply those exponents. So t to the 15. So r to the 6th divided by 8 times t to the 15. So again, just to reiterate, the rule is that if you've got a power of a power, you're going to multiply the exponents. If you've got an exponent over top of a product or a quotient here, then you can distribute that exponent to the factors or to the dividend and the divisor there. What you can't do, and I cannot overstate this, a plus b to the x, please don't distribute that. That does not work. It's not true. Before you could do that sort of distribution here, you'd have to do the addition. What's inside the brackets first? I'd have to add first before I could do that. And because I don't know what a plus b is, I got to stop. I can't move forward with that particular question. That's it.
The zero law.
Okay, well, now we're going to take a look at the zero law. This isn't so much about, how do I say this? This isn't so much about introducing you to like a law of exponents, as much as it is just reminding you not to make a goofy mistake. X to the 0 is equal to 1, not 0. Okay, this is not x multiplied by 0. It's x raised to the exponent 0, and that has to be equal to 1. Now let me show you why that has to equal 1 here. It's a very simple little pattern here. If you've got 2 cubed, that's 8. 2 squared is equal to 4. Now, what I did here is I dropped the exponent by 1 and then divided, over here I divide by 2. 2 to the 1 has got to be 2. I drop the exponent by 1, I divide by 2. So now drop the exponent by 1 again and I get 2 to 0. Divide by 2 and you get 1. Now that works with any base whatsoever. If you've got 3 cubed, that's 27. 3 squared is 9. Okay, 3 to the 1 is 3. Now at every step along the way on the right hand side, I'm dividing by 3. With every step along the way, I'm subtracting 1 from the exponent. So when I go to 0, again the answer is just 1. So anything to the power of 0 is going to be equal to 1. Now I state that. However, what happens is a lot of times on exams when there's a little bit of pressure, that error gets made all the time. Okay, people make that x to 0. Additionally, by the way, the same sort of error gets made here. 3 squared, okay, 3 squared is not 6. It's not 6, it's 9. 3 squared is 9. Okay, but it's the same error. It's people thinking, oh, I just multiply those. No, you don't. This is not 3 times 2, this is 3 times 3. This is x multiplied by itself, essentially, never, like not a once here, but if you look at the pattern here, that has to be equal to 1. Okay? Now, let's take a quick look here at some of these examples. So 5 raised to the power of 0 has got to be 1. Negative 5 to the power of 0 has to be equal to 1. Now, let me rewrite this. If this is negative 5 to the 0 without the parentheses there, then the answer is negative 1. Because what happens here, now think about this. This is like negative 1 multiplied by 5 to the 0. Order of operations tells us that we do the exponent first. So 5 to the 0 is 1, and then I multiply by the negative. Now up here, order of operations tells me that I do what's inside the brackets. So the negative 1 and the 5 become one value, negative 5. Then I raise that to the power of 0. And that's why this becomes positive 1. Okay, very subtle difference, but man, does that ever screwed up a lot of people. Particularly when you go to the calculator and enter this in. Okay, I'll ask people to enter this into their calculator. I'll ask them to enter in this parentheses -5 parentheses 0, and they think they're doing it when they enter this in, when they enter just -5 to the 0, and they get the wrong answer. Or they'll get, for example, if they get -2 squared, okay, and they enter that in the calculator, they're thinking, well, that should be positive. It should be positive, -2 squared, but the negative's not being squared here. Order of operations says that this is -1 times 2 squared. 2 squared happens first, and then you multiply by 1, the negative, to get -4. Anyway, it's just a little error, a little misunderstanding, but it can be really frustrating, okay, when people do that. And, people get really mad with themselves, and a lot of times they assume, well, I can't do math, I don't get math. But it's just these little errors. We just want to clean that up. Over here, again, bear in mind what's going on here. Order of operations is like -1 times 2 times a to the exponent 0. Well, that has to happen first. So a to the exponent 0 is going to be 1, and then that gets multiplied by the -2, and the answer here is going to be -2. Okay. Now over here, all right, order of operations would say do whatever's inside the brackets here first, simplify that out here. There's nothing to do. There's no like bases here, so there's nothing to simplify. And it doesn't really matter, because this whole thing here is being taken up to the power of 0. Doesn't matter. That's going to be equal to 1. Doesn't matter what the base is, unless the base is 0. Okay? Just note here that if you've got 0 to the power of 0, this is another one of those little undefined things. Not quite clear what that is. Okay? And you'll see that when you get to a calculus course here, you look at how this sort of a pattern might show up and what you would do to it when you're dealing with what we call limits. But anyway, big idea here right now, though, is that you got a base here. As long as it's not 0, base to 0 is always going to be equal to 1.
The negative exponents law, or the integer exponents law.
All right. Negative exponents. Here's another one that, again, we're assuming you've seen before, okay? Because this was something that you would have seen back in grade 10, not typically. Negative exponent law. So if you've got a to the -1, this is the same as 1 over a to the 1. So a negative in the exponent causes a reciprocal, okay? It causes the power to move from the numerator, let's say, so this is like a to the -1 over 1. It causes that thing to move down to the denominator. If it's in the denominator, okay, that negative causes this thing to jump up into the numerator. Basically what happens is the negative causes the expression here, the power, to move from one side of the division statement, or the division sign, to the other here. Another way that we might look at this here is if you've got a over b, let's say to the power of -1, this would be the same as b over a to the power of 1. That negative causes the base here to reciprocate. And that's how we get rid of it. This is not, okay, a to the power of -1 is not -a. Okay, this is not a multiplied by -1. It doesn't matter how strongly you feel it should be that way. If you feel that way, I'm sorry, you're wrong. It's not. A to the -1 does not equal -a. And let's go back up here and I'll show you why. We set up this pattern here when we were looking at the 0 law. So subtract 1 from the exponent, then we divide by 2. Subtract 1 from the exponent, divide by 2. Subtract 1 from the exponent, divide by 2. Now, subtract 1 from the exponent and divide by 2, and we're going to get 1/2. Well, there you go. 2 to the -1 is equal to 1/2. Subtract 1 from the exponent, and then you're going to end up with 1 over 2 squared, because you're dividing by 2 again. And so, whoops, sorry, that should be negative 2 there. So we subtract 1 from the exponent here, and the pattern holds. As soon as you get past the 0 there, the pattern still holds. Subtract 1 from the exponent, divide by an extra 2 there. And that's why that pattern holds. Now let's take a quick look at some examples here. We've got 2 over 3 to the -4. Now, that negative is going to cause a reciprocal. Now, all I've done is apply the negative. I still haven't dealt with the 4 yet. But the negative exponent here causes a reciprocal to the base here. Now, based on a previous law, I know that I can take that exponent here and distribute it to the dividend and the divisor here to make this 3 to the power of 4 over 2 to the power of 4. In other words, 81 over 16. And that's what we're looking for. Over here, now, okay, this is a bit of a tough one here, because this is what I would do with this one. First of all, I'm seeing the division here. I've got a power of m divided by power of m. I would see this as m to the negative 3 minus, for the subtraction, for the division there, negative 2, because that's the exponent in that term in the denominator. Negative 3 minus negative 2, well, it's going to be negative 3 plus 2, or m to the negative 1. Now, all I really have here is an expression with a negative exponent. I would write that as 1 over m to the power of 1, and I don't have to write it if it's 1, right? The assumption is if you're not seeing the exponent, it's 1. Okay? So that's one way of doing it. Another way of doing it, or you could see it as the m to the negative 3, m to the negative 2. We could deal with the negative exponents first, bearing in mind that what that negative means is it's taking in each of those individual powers and moving them to the opposite parts of the fraction or the rational expression. So m to the negative 3 is going to drop down to the denominator as m cubed. M to the negative 2 is going to jump up to the numerator, m to the negative 2 is going to jump up to the numerator as m squared. Okay, now I can simplify this and make this m to the 2 minus 3, which is again m to the negative 1, and we've already seen that takes us right back to here. Okay, let's take a look at this third one here. Negative 2x to the negative 3 over x squared. The negative 2 is not part of the base. Okay, the power is only x to the negative 3. That's it. So the negative 2 is going to sit out front. It's just going to be happy, just sitting there doing squat. But I've got division here. I've got x to the negative 3 divided by x squared. So that will be x to the negative 3 minus 2. Okay, and now when I've got, again, with division there, I'm subtracting the exponents. So this will be negative 2x to the negative 5, it looks like. And then to get rid of the negative in the exponent there, which isn't absolutely necessary, please don't get me wrong, but it is something at this point that we're kind of expecting you to do with this exponent there. That negative exponent is going to take that power and move it to the other part of the fraction, or the rational here. So this will come down to the denominator. Now again, remember, the negative 2 didn't move because the negative 2 was not part of the base. There was no parentheses around it. If there's, in the absence of the parentheses, it's just whatever symbol is right below the exponent. That's the base. Over here, now, order of operations tells me that what I'm going to do here is I'm going to deal with what's inside the parentheses first. I can't really simplify these two powers by combining them because their bases are different. But I've got a y to the negative 3 in the denominator. The negative is going to force me to move this to the other part of the rational. So this will be x squared. X squared is not going to move because it doesn't have a negative exponent. But the y to the negative 3 here is going to bump up, become y cubed. And then this will be cubed up top there. Okay, now I've got two products. My mistake. I've got a product. I've got two factors that are part of the base of that overall power. So the 3 is going to distribute. I'm going to have x squared cubed, which will be x to the 6th. Y cubed cubed, I'm just going to multiply those together to get y to the 9. And so there we go. That's the expression we're looking for. Now, again, just to reiterate what's going on here, the negative exponent does not make the term negative. It's not a multiplied by negative 1. It's a to the power of negative 1 that causes a reciprocal. Okay, so it's either going to move from the numerator down to the denominator, or from the denominator up to the numerator. Or you can think of it as just taking whatever the base is there and causing the base of that power there to reciprocate.
The fractional or rational exponents law.
All right, now let's try to remind you what goes on here when you've got fractional exponents here. When you've got x to the power of 1 over m, that becomes the mth root of x. Okay? Or another way of saying that if you've got x to the power of this rational exponent here, m over n, that is the nth root. Okay, the denominator becomes the root index, and the m is going to become the exponent on that power there. Or, I mean, order doesn't matter here, so like you can think of this as either the division here or the multiplication here of the m. Actually, that's probably not a good way to think about that. But you basically what's happening here is you could think about this as, let's say, x to the m to the 1 over n, or you could think of this as x to the 1 over, n to the m. Essentially, you can do the power first and then the radical, or the radical first and then the exponent here. Honestly, I recommend this one more often than not when you're simplifying, because it's easier to reduce that number and then make it bigger than it is to make that number even bigger and then try to take that radical. It doesn't matter what order you do those in, but this is almost always the better way of doing it. Now, just to quickly explain why this rule is like that, if I've got x to the 1/2, and I'm just going to use this as an example, and I multiply by x to the 1/2, I know that when I multiply two powers together that have the same exponent, this is going to be x to the 1/2 plus 1/2. That's just going to be x to the 1. Okay. Now I got to ask myself what this is equivalent to. Well, when I multiply this value by itself, I get x. So x to the 1/2 times x to the 1/2 is equal to x. So those two terms here, or think of it like this. Another pattern very similar to this that we've seen before is if I've got the square root of x and I multiply that by the square root of x, I am going to get x. Because that's what a square root, I mean, that's what we mean by a square root. This multiplied by this gets you that. Okay, gets you that value that's underneath that square root here. So because these two products are giving us the exact same result, it must be the case that x to the 1/2 is the same as the square root of x. And that idea can be generalized to cube roots, fourth roots, fifth roots, and so on. So that's the pattern here. I know for a lot of people that's a difficult one. I know the exponent laws can be very tricky, okay? Because by this time you've learned a lot of algebra, and now it's just the exponent laws can sometimes be a little tricky because they're not obeying or doing exactly what you might think they should do, and so on and so forth here. And when you throw a fraction in the exponent, that just makes it worse. All I can advise you here is that when you're going through these problems, just kind of stop, take a breath, relax, get focused, make sure that you know what you're doing. Don't rush into these problems here, because oftentimes when you make a mistake here, it's not because you've misunderstood, not because there's a radical misunderstanding here, but because there's that was a bit of a joke here, a radical misunderstanding. So I didn't even notice that until just now. Haha, because these are called radicals and misunderstand. Well, whatever. I'm sorry. Anyway, don't beat yourself up. Just stop, slow down, and figure out what's going on here. So let's just take a look at some examples here. I've got 25 to the 1/2. Okay, that corresponds to a square root of 25, and the square root of 25 is just 5. There's my answer. Now, not plus or minus 5, just 5. There's a subtle difference here. If I was to ask you x squared equals 25, then my answer would be plus or minus 5. Because to square something gets rid of the negative, okay? So x could have been either positive or negative. But when I ask you x is equal to the square root of 25, this is a different question well, not altogether, but it is a different question, okay? They are related, obviously, but they are different, okay? Here I'm just asking for what value multiplied by itself equals 25, but I'm only interested in the positive number, what we call the principal square root. Okay, and that's because this symbol right here can only ever produce a positive result. That's a rule that you want to follow fairly closely. Let's take a look at this next one here. This is going to mean the square root of 36 cubed. Okay, well, the square root of 36 cubed, I suggest the order that you do this in is going to be the square root of 36 and do the cubing later. And the reason I say that is because I don't want to have to cube 36 and then take the square root of that. However, I am very comfortable taking the square root of 36 and just getting 6. Okay? And then 6 cubed is going to be what? 6 6 times 3 is 18. 216 is going to end up being the value of this. See, it's easier to do it this way, to take that square root first and then make that result bigger than it is to go the other way here. So denominator becomes the root index. The numerator becomes the overall exponent. In a case like this, when they throw a variable down there, basically we're just asking you to write out what this is in a different form. So this is going to end up being the cube root of a squared, or, like I said, the cube root of a, and you can either do the squaring within the radical or outside the radical. And again, that tends to be easier to work with. Over here, here's another case here where I've got this fractional exponent here, but it's only on the x. The negative 3 has nothing to do with it. So the negative 3 just sits there separately on its own. It's not affected by anything. Now, I know that this is going to be a fifth root, but notice the negative in front of the fraction here. That negative is going to push that to the denominator, so this will become the fifth root of x in the denominator. That's what the negative does. That's a previous rule there. And then the 1/5 becomes the fifth root there. Okay, so again, just to reiterate the rule here, if you've got x to the m over n, that is the nth root of x to the power of m, or the nth root of x, all to the power of m. It doesn't really matter what order you do those in.
Simplify each of the following and leave all answers with positive exponents. b to the fifth times b divided by b squared.
Okay, so here we're going to put these all together here. Now, the rule here, or the expectation that we're going to put these all with positive exponents, that isn't a rule per se. But in this particular question, it's the expectation. So yeah, if you end up with a negative exponent, we just want to get rid of it. But that's not always the case. It's not always required that you get rid of negative exponents here. Now, let's write this out here. And let's just put the pieces together. In the numerator, I've got b to the 5 times b to the 1 here. So that is going to end up becoming b to the 5 plus 1. Okay, and I would see that over b squared. So I've simplified the numerator here. Now, the division, we know that division means I'm going to subtract the exponents. So even without doing this addition right here, I know that this is going to end up becoming b to the 5 plus 1 minus 2. So I could almost have jumped directly to this. I just want you to understand this. You don't have to go through and do this step by step by step, particularly with stuff like this where it's all multiplied or divided together. Okay. I've got the multiplication I'm going to add, and then I'm going to subtract that. So 5 plus 1 is 6, minus 2 is 4. So the answer here is b to the power of 4. Okay. I could have actually done that right from here. I could have jumped right to that answer there. But just bear in mind what the steps are that we kind of go through in our head to get to that point.
Y to the 7th divided by y squared cubed.
Okay, so this one right here. Before we jump into this, just to remind you of something that you've probably looked at a long time ago, but may have forgotten at this point here. That bar, wait, what does it mean? Well, it means division. Yeah, but it also implies a set of brackets, okay, around the numerator and the denominator. Now, in the previous question, that set of brackets was here as well, but it wasn't such an issue. It didn't really matter in this particular question. It matters a little bit here because it helps us organize our thoughts a little bit. Because remember, order of operations says do what's inside the brackets first. So I'm going to simplify what's down here in the denominator first before I do the division. So this will become y to the 7 over, well, I've got a power of a power, so I'm going to multiply the exponents together. So y squared cubed, this will be y to the 6th. Okay, now remember, this isn't, by the way, this isn't 2 to the 3. This is 2 times 3 because they're both in the exponent. Now that I've dealt with what's inside the parentheses there, now I can do the division. And when I divide, I'm just going to subtract the exponents. And so 7 minus 6 is 1. Okay, and if the exponent's 1, I don't have to do anything. I would just leave it just the way it is.
B squared cubed multiplied by b to the 4th to the 4th.
Okay, now here's another question where, again, the consideration here has to be towards the order of operations. I'm multiplying two powers together, but I got to deal with the exponents first before I can do the multiplication here. So I've got a power of a power, so this will end up becoming b to the 2 times 3 is 6. And this is going to be multiplied by b to the 4 to the 4, and that's going to end up being 16, the product of the two exponents. And now this becomes an example of the product law here. B to the 6th multiplied by b to the 16 will be a power of b, and I get the exponent by simply adding the exponents from the above two powers together, the two factors. So there we go, and we get b to the 22.
3x to the 6th, y to the 5th, all squared.
Okay, now for this question again, I'm seeing a set of parentheses here, so that would inspire me to look inside and do whatever kind of simplification I need to here first. But there's nothing to simplify. This is 3 times x, a power of x times a power of y. There's nothing there that can be simplified because there's no like bases. So I can apply the power rule here. That 2, because these are all factors here, the 2 will distribute to each one of those. So this will become 3 squared. Oops, sorry, not y to the 6th, x to the 6th. X to the 6th squared. And then this will be y to the 5th squared. Okay, well 3 squared is 9. I've got a power of a power, so this will become x to the, well, product of those two, so 12. And another power of a power, so the exponent will just be the product of those two exponents, so y to the power of 10. So 9x to the 12 times y to the 10.
Negative 3m squared n multiplied by negative 4m to the 4th n to the negative 2.
Okay, so now we've got two sets of brackets here, which would imply that what I'm going to do is try to simplify whatever's inside those brackets first. But there's really nothing to simplify because they're all different powers. There's no common bases there. So what I'm going to do now is transition over to just the product of the two. Now, there's no addition or subtraction here. Okay, and I say that again. There's no addition or subtraction. I know what you're seeing there, that negative there, but that's not a subtraction. Okay, that's a negative sign in front of a term, but it's not being added or subtracted to anything. So there has to be multiple terms for addition subtraction. Okay, so in this case there's just one term here, one term here. So when I multiply these out, this is not a matter of distribution. I'm just multiplying them out here. Now the easiest way to do that is to multiply the parts of the two terms here that have the same basis here. Now, when it's just numbers, just coefficients, I don't have to worry about that. I know what negative 3 times negative 4 is. That's positive 12. Now, I've got a power of m and a power of m. So that'll be m, and then what I'll do there is I'll add the exponents. So 2 and 4 is going to give me 6. Now I've got two powers of n. This is n to the 1. Remember, if you're not seeing it, it's a 1. And then negative 2. And if you add those together, 1 and negative 2, you'll get negative 1. Except that the restriction in this particular problem is that we write everything with positive exponents. So I've got an issue here with this negative exponent. But it's just a negative 1. And we know that the negative is just going to cause that factor there to jump into the denominator. So I'll get 12m to the 6th over n. And that's the answer we're looking for here.
b to the 5th multiplied by b to the negative 1 divided by b to the negative 3.
Okay, once again, we want to concern ourselves with order of operations. The bar there implies parentheses around the numerator and the denominator. So I'm going to simplify what's up in the numerator first. I've got two powers multiplied together. So I'm going to add the exponents. So this will be b to the power of 5 plus negative 1. So b over 4. And then there was nothing to simplify in the denominator. It was what it was. So just b to the negative 3. Now, the issue here is the division. So I've got b to the 4 divided by b to the negative 3. So this will be b to the, well, it's going to be the difference between those two. Now let's make sure we write this out carefully. This will be minus negative 3. Don't let that negative fool you into thinking, oh, they've already put a negative there, and then still go 4 minus 3. This can't be 4 minus 3. It's 4 minus negative 3. Okay? And 4 minus negative 3 is going to be a 7. So the answer here is going to be b to the 7. Be very, very careful, very deliberate, okay, with the integer work that you do. We already know that negatives are going to cause a fair bit of problems for a lot of people, okay? But just take it easy, okay, and you won't get caught in those little traps.
5mn cubed divided by 4m squared n, all to the power of 2.
Okay, now for an example where order of operations really is kind of obvious here. I've got this set of parentheses here. I'm going to simplify what's inside there first. We'll do that squaring later there. Okay, now my coefficients, I've got a 5 and a 4. Yeah. Well, not a whole lot I can do with that. So this is going to end up being 5 over 4. That's going to stay the way it is. Now, I've got powers of m here. I've got m to the 1 over m squared. So now I'm going to subtract those. So this will be m to the 1 over m squared. So that's going to be 1 minus 2, or m to the negative 1. And then I've got n cubed divided by n. And again, if there's no exponent shown, it's 1. So n cubed over n to the 1 is going to be n squared. Okay, so here we go. So 5 over 4, m to the negative 1, n squared to the 2 here are all squared. Now, that m to the negative 1, I might as well deal with that right now. I might as well. That's going to move that into the denominator, so this will become 5n squared is all that's left up there, and I've got 4m in the denominator. And that's all going to be squared. Because there's no addition or subtraction here, I can distribute that square to every factor, okay, in the dividend and the divisor here. So this will become 5 squared, which is 25. N squared, which will be n to the 4. I'll just multiply the exponents together. 4 squared will be 16. And m to the 1 squared will just give me m squared. And so that's the answer that I'm looking for. 25 n to the 4 divided by 16 m squared.
M cubed n to the negative 2 divided by 3m n to the 4th squared times m to the 5th n squared.
Okay, so there is a little bit more going in this question. This one's kind of stepped it up a little bit. What we're going to do first of all is put the parentheses around the entire numerator and denominator, just because that's what that bar implies. And so now, there's nothing much I can do, in the numerator here. It'll be m cubed n to the negative 2. But in the denominator, there is some stuff I can do. I'm going to multiply these two together, but what I got to do first is simplify what's in the exponent, what's in the parentheses here. But I really can't. This is 3m n to the 4. Well, there's nothing that's like. There's nothing I combine there because there's no like bases. Same thing for this second set of parentheses. There's nothing there that's like. But before I can multiply these two together, I have to deal with this exponent, the one that's on the full term here. So now everything here is going to get squared. So 3 squared will get me 9. M squared will just be m squared. N to the 4th squared, well, now that's a power of a power, so this will be n to the 8th. I multiply the exponents together. What I got to remember here is that square distributes to each factor. And now this is still multiplied by m to the 5th n squared. Now that I've dealt with that exponent there, now I can multiply out the entire denominator. Now the numerator is still going to stay the same, m cubed n to the negative 2. There's nothing that I can put together with a 9, so that's it. But I've got m squared, m to the 5th, so this will be the sum of those two, m to the 7th. N to the 8th, n squared will be n to the 10. All right, now we've made some significant forward steps there. We've got that reduced down quite nicely. Now, what I've got here is, in terms of the coefficient, there's really not much I can do. The 9 is going to stay in the denominator. Okay. Now, look at the numerator here. I've got a power divided by a power, so I'm going to subtract exponents. So that'll be m to the 3 minus 5. That's m to the negative 2. Over here, this will be n to the negative 2 divided by n to the 10. Division is going to end up being subtraction. Negative 2 minus 10 will be negative 12. Okay, now finally, because the question told me to deal with negative exponents, both of these powers here have negative exponents. They're both going to switch to the other side of the expression here, the other side of the division sign there. The 9 isn't going to move. Now, if everything moves out of there, you're still left with a 1. And this will end up being 9 m squared n to the 12. Okay? Because bear in mind, there's a 1 multiplied out front there, and it's not going to move. It's not written in this one right here, just because it's assumed. So there we go, 1 over 9m squared n to the 12th.
Negative 2x squared divided by 3y, all to the power of negative 3.
So this question right here, I would be tempted to do whatever I could to simplify what's inside there first, but there's nothing I can do. There's no simplifying of the coefficients, and the powers don't have the like base there. There's nothing I can do. So I'm going to move to the outside exponent here. Now there's two parts to this. There's the negative and the cube. I'm going to deal with the negative first. And we know, based on previous experience here, that what that negative is going to do is going to reciprocate the base. So this negative 2x squared over 3y is going to become 3y over negative 2x squared. Now the negative can go anywhere, by the way. That negative can be bounced around. The fact that I've moved it to the denominator is just because I think a lot of people would do it like that. But it can stay in the numerator if you want. It doesn't matter. Now, because there's no addition or subtraction here, everything is going to get cubed. The 3 is going to get cubed. The y is going to get cubed. The negative 2, the negative is going to get cubed. The 2 is going to get cubed. So let's just do that as negative 2 cubed. X squared cubed. Whoops, sorry, can't see that. Now, 3 cubed is 27. Y cubed is y cubed. Negative 2 cubed is going to be negative 8. X squared cubed. Okay, power of a power, you're going to multiply the exponents. That'll be x to the 6th. And then what will likely happen is you either want to move the negative out front or move it up to the numerator. It doesn't really matter. It looks a little goofy when you write it in the denominator, though. It looks better when it's either out front or up on the numerator. So that's essentially the answer that we're looking for. Negative 27y cubed over 8x to the 6th.